This is following on from Australian magpies to defining minerals, and this is the slide that we finished with in that video. So we've looked at minerals being defined by composition and structure, so that's chemical composition, and the atomic structure. Okay, so we can now go on to the composition and groups of minerals. And I don't expect you to remember this, off by heart. There is no need to do that. You can always look things up. But I do want you to understand that the overwhelming proportion of the Earth, so I'm using percentages here, is made up of very few elements, and those are iron, oxygen, silicon, manganese, nickel, sulfur, calcium, aluminium, chromium, sodium, potassium, and titanium. Now, I make no apologies for using chemical element symbols because to write them out in full is unbelievably tedious, and you really should get to know what some of the common ones are. I'm not going to be going into esoteric things like Rutherfordium, okay? Now, these common elements, and there aren't many of them when you look at the periodic table, they're not found on their own. Okay, now you can get O2 and O3 in the atmosphere. You can get pure iron metal, but most of the time these things do go around as compounds of some form, and they form molecules with other elements. So you have oxides, silicates, aluminosilicates, and sulfides and oxides are oxygen added to something else. Silicates are a silicon and oxygen added to something else. Aluminosilicates are aluminium, silicon, and oxygen. And sulfides have no oxygen. They're sulfur, like lead sulfides, or fool's gold is lead. Iron sulfide is fool's gold, or you may know it as pyrite. So those form groups of mineral types. These are mineral types, the oxides, silicates, and these are the commonest mineral types that we found in the planet. If you are dealing entirely in surface environments, I'm talking about the planet as a whole, but if you're talking about surface environments, you've got to add carbon and hydrogen into these 12. Because in surface environments, obviously, we have to take these into account, mainly because of the biomass, of course, adding the C and the H in there, okay? But in rocks terms, you get carbonates because of the carbon. That's the carbonate ion is quite a common ion. So that's the rock I'm thinking of is CaCO3, so it's the CO3 bit. The carbon and the oxygen is the carbonate. And of course there's loads of dissolved carbonate in the oceans, and this is one of the buffering reactions within the ocean to help buffer the acidity, is the carbonate reaction. But we know carbonates as limestones, as that sort of a limestone rock is made of carbonates. And also chalk. Some people will know about chalk, which is a type of limestone. So also, because you're in a surface environment, you don't just get sulfides, you get sulfates as well, because you are in a slightly different environment. So we have to add that in, and you'll be coming across, after I've finished, you'll be focusing much more on surface environments, because after all that is much more pertinent to where we are living. Now, I do just want to, let me just check, yep, let me just go that way. I do just want to show you that you do, when you come to your tute rooms, you do pass, like next door, you do have your own museum and a rock and mineral gallery next door to that, so that's through there. And you also have loads of interesting displays that John, who is the museum curator, has set up. Now, the museum is open most days, and the Rock and Mineral Gallery is open most days when John is in, but I think it's definitely open Monday, Wednesday, Friday. And also friends of the museum come in a voluntary group, and they open it at weekends for the general public, because it is a general public facility that the university has. And it is very interesting. There are some beautiful specimens in the museum, but there are also some, they're arranged in a logical mineralogical order, and John is a mineralogist. He's a micromineralogist. He's very, very friendly when he has time, and he's really quite delighted for people to have a look around. So go in and have a look around. There's obviously fossils and things. Our Argyle diamond got stolen, unfortunately, but you know, such is life. So do have a look around here. Now, I'm just going to go into igneous crustal rocks. Igneous, and you know what this means because it comes from the same root. The root comes from the same word as ignite, meaning to set fire to. These are volcanic rocks, igneous rocks, what you would call volcanic rocks, fiery rocks, you know, born of fire. And crustal means that I'm looking specifically at them in the crust. And as you know, there's two flavours of crust. There is continental crust and there is oceanic crust. And I've given you an image here of your average, the most common igneous rock perhaps that you will see, certainly on the south coast of WA, and certainly in the hills where you see rock exposed above the Darling Scarp. And this is what people refer to as a granite. I'm a little bit twitchy about that because a granite is actually a very clearly defined rock. It has to have a specific percentage of certain minerals in it, and very few rocks that you will see will be granites, but they can be granitic, you know, or a granitoid, i.e. granite-like. And indeed we have a further bucket terminology that we use, which is felsic. Felsic, by the way, is a contraction of feldspar and silica. Okay, and you'll see that granitic rocks have feldspar and quartz in them. And quartz, as I'm sure everybody knows, SiO2 is made of silica and oxygen. It is the silicate. All right, so any rock that's primarily composed of feldspar and quartz, we refer to as felsic, which is a contraction of these terms. And you can think of things as being generally granitic. All granitic rocks are felsic, but not all felsic rocks are granitic. Okay, so it's just another bucket term you may come across. Now, don't worry too much about the mineral names. I'm just trying to explain it for those of you who like things linked. Look at the elements. So we have potassium, sodium, and calcium, aluminium silicates, okay, which is the feldspars. So we have potassium, sodium, calcium, aluminium, silicon, and oxygen. That's a common mineral. Feldspars. We have quartz, silicon and oxygen, and we have micas, which can have some iron or potassium in them. They've also got OH, which is the equivalent of water, H2O, in the crystal lattice, and they're aluminium silicates. On the other hand, we've got oceanic crust, which generally is basaltic, which basalt would be the rock type, and believe me, the ocean floor is floored with basalt underneath a thin veneer of sediments. Depending on whereabouts you are, depends on the thickness of the sediments, depends on how old the crust is as well. Now, basalts, okay, they have a different mineralogy. They have clinopyroxene in them, which isn't mentioned over here, but they do have plagioclase feldspar in them, which is mentioned over here. However, look at the elements. Okay, they have plag, which tends to be the calcium, which is the calcium, sodium, aluminium, silicon, oxygen, which is the same as the granitic rock, but they don't tend to have this potassium end member in. That's not really there. And in the pyroxene, they have iron and magnesium and silicon and oxygen. You might get a sniff of iron up here, but not much. So immediately you're thinking, well, okay, if these are the minerals in basaltic ocean crust, then it should be heavier. It should be more dense. And it is. It's 3 grams per cubic centimetre as opposed to 2.6 grams per cubic centimetre for the granitic rock. And these are averages, don't forget. And you may think 0.4 of a gram per cubic centimetre is not a shed load of difference, not even an Australian SI shed load of difference, okay? It is, especially when you're looking at the volume of material that you have. And it really, really, really does affect the way that the plates behave. Continental crust generally does not subduct. You can get erosion of continental crust into sediments that actually then go, some of which will go down the subduction zone, but most of which, as you saw, get scraped off and accreted as a prism, an accretionary prism to the side of the continent. This stuff is heavier than the mantle when it's cold, and it will subduct, heavier than the shallow mantle. It also has this underplated material to it that is even heavier, and it will go down. Okay. However, we can look at Earth's mean density again, because both of these are considerably less than Earth's mean density. And don't forget, that means it's average sort of density, which means that as these two are both lighter, that means that, that there's some very much more heavier material in the Earth, perhaps. But remember that the crust is a tiny, tiny, tiny component of the Earth. Volumetrically, we should be ignoring it. And that the majority of the mantle, for instance, is made of magnesium, iron, silicates, the upper mantle, and magnesium and iron oxides in the lower mantle. Okay, but we know that in the core, much more of the heavier metals are in the core. All right, so that's good. Now, go to a periodic table. This is from Los Alamos, which is a very good, a very interesting periodic table site to go to. It's all interactive, and when you click on these, it goes to a page which has the most fascinating information about them, to be honest. Anyway, what I've done here, and you don't see the animation because I'm doing it in screenshot, because I am running something else on my other screen. I am multitasking, I'm afraid. So in here we have got in red, which looks a bit purplish here next to the blue, we've got the elements that I mentioned as appearing in granite. So that's sodium, potassium, calcium, aluminium and silicon. Okay, and then I've added to them magnesium, calcium and iron, which are the elements that are commonly found in the basalt, and obviously silicon should be blue as well. And I've missed out oxygen up here because all of the minerals in both flavours of crust have oxygen in them. So you can see straight away that it is iron. The atomic weight of iron is considerably higher than the other elements that are commonly making up the minerals in the crust. And so this alone is the reason why the oceanic crust is so heavy. Okay, sedimentary crustal rocks. Now, previously we were looking at igneous crustal rocks. Now we're looking at sedimentary. There are three categories of rock, which is igneous, sedimentary and metamorphic. Sedimentary means that they are produced at the surface of the Earth. They are generally clastic rocks. That is, they are rocks that are formed by breaking bits of other rocks off, fragments of other rocks, or mineral fragments where a rock has broken down a lot. And it's the size of the fragments and the type of the fragments that gives the rock its name. Now, there are also chemical precipitates, and there are also volcanic